When dealing with electrical installations, especially feeders supplying panel boards, it's crucial to understand the overcurrent protection requirements outlined in the National Electrical Code, or NEC. In a scenario where a 200 amp feeder supplies a 100 amp panel board, the question arises whether 100 amp fusing is required at both ends of the feeder. The answer is yes, the feeder does require 100 amp fusing at both ends. This is primarily dictated by NEC Section 240.21b3, which mandates that overcurrent protection must be provided at each end of a feeder. Let's delve into the reasons behind this requirement and explore the relevant NEC sections. The primary purpose of overcurrent protection is to safeguard the electrical system from damage due to overloads or short circuits. An overload occurs when the current exceeds the ampacity of the conductors, causing them to overheat and potentially leading to insulation failure or even a fire. A short circuit, on the other hand, is a low resistance path that allows a large amount of current to flow, which can cause immediate and severe damage to equipment and conductors. In the given scenario, the 200 amp feeder is supplying a 100 amp panel board. The panel board itself has a maximum overcurrent protection rating of 100 amps, as specified in NEC Section 240.85. This means that the panel board is designed to handle a maximum current of 100 amps safely. If the current exceeds this value, the panel board's internal components could be damaged. To protect the panel board from overcurrent, 100 amp fuses are required at both ends of the feeder. The fuse at the supply end of the feeder protects the feeder conductors from overloads or short circuits that may occur downstream, while the fuse at the panel board end protects the panel board itself from overcurrent. Consider the following scenario to illustrate the importance of fusing at both ends. Suppose a fault occurs within the 100 amp panel board, causing a short circuit. If there is no overcurrent protection at the panel board end of the feeder, the entire 200 amp capacity of the feeder could flow into the panel board, potentially causing severe damage or even a fire. However, with a 100 amp fuse at the panel board end, the fuse will quickly interrupt the flow of current, preventing the panel board from being damaged. Similarly, if an overload occurs on one of the branch circuits connected to the 100 amp panel board, the 100 amp fuse at the supply end of the feeder will protect the feeder conductors from overheating. Without this overcurrent protection, the feeder conductors could be damaged, leading to a potential fire hazard. It is important to note that the overcurrent protection devices must be properly sized and selected for the application. The ampacity of the conductors must be equal to or greater than the rating of the overcurrent protection device. Additionally, the overcurrent protection device must be of the correct type for the application. Fuses and circuit breakers are the two most common types of overcurrent protection devices. Fuses are one-time devices that melt and interrupt the flow of current when an overcurrent occurs. Circuit breakers, on the other hand, are receptacle devices that trip and interrupt the flow of current when an overcurrent occurs. The choice between fuses and circuit breakers depends on the specific application and the preferences of the installer. In general, fuses are more reliable and provide better protection against short circuits, while circuit breakers are more convenient to reset after an overcurrent. In addition to NEC Section 240.21b3 and 240.85, several other NEC sections are relevant to feeder overcurrent protection. NEC Section 240.4 specifies the general requirements for overcurrent protection of conductors. This section requires that conductors be protected against overcurrent in accordance with their ampacities. NEC Section 310.15 provides tables that list the ampacities of various types of conductors. NEC Section 240.6 specifies the standard ampere ratings for fuses and circuit breakers. This section ensures that overcurrent protection devices are readily available in the required sizes. NEC Section 240.15 specifies the requirements for the location of overcurrent protection devices. This section requires that overcurrent protection devices be readily accessible and located where they will provide the best protection for the electrical system. In summary, the 200 amp feeder supplying a 100 amp panel board requires 100 amp fusing at both ends to protect the panel board and the feeder conductors from overcurrent. This requirement is based on NEC sections 240.21b3 and 240.85, as well as other relevant NEC sections. It is essential to follow all applicable NEC requirements when installing electrical systems to ensure safety and prevent damage to equipment. Always consult with a qualified electrician or electrical engineer to ensure that the electrical system is properly designed and installed. Now let's expand on some additional considerations for feeder overcurrent protection. Firstly, the specific type of overcurrent protection device, whether a fuse or a circuit breaker, needs to be chosen appropriately for the application. Fuses offer the advantage of being a simple, reliable, and generally faster acting overcurrent protection method, especially for high fault currents. They operate by melting a fusible link when the current exceeds their rating, interrupting the circuit. Circuit breakers, on the other hand, offer the convenience of being resettable. They trip electronically or thermally when an overcurrent condition is detected and can be reset after the fault is cleared. The choice between the two often depends on factors such as the criticality of the load, the frequency of potential overcurrent events, and maintenance preferences. Secondly, the ampacity of the feeder conductors must be carefully selected. NEC Article 310 provides detailed guidance on determining the ampacity of conductors based on factors such as the conductor material, insulation type, installation method, and ambient temperature. It is crucial to ensure that the feeder conductors are adequately sized to carry the intended load current, with sufficient margin to account for potential future increases in load. Furthermore, the overcurrent protection device should never exceed the ampacity of the conductors it is protecting. If the overcurrent protection device is rated higher than the conductor ampacity, it could allow the conductors to overheat and potentially cause a fire before the overcurrent device trips. Thirdly, the location of the overcurrent protection devices is also important. NEC Section 240.21b provides specific rules for the location of overcurrent protection in feeder taps. In general, the overcurrent protection device should be located at the point where the feeder receives its supply. However, there are exceptions to this rule, such as when the feeder is tapped to supply a smaller load. In these cases, the overcurrent protection device may be located at the tap point, provided that certain conditions are met. Fourthly, coordination of overcurrent protection devices is essential for ensuring selective tripping. Selective tripping means that only the overcurrent protection device closest to the fault should trip, while upstream devices remain closed. This helps to minimize the disruption to the electrical system and allows other loads to continue operating. Coordination studies are often performed to determine the appropriate settings for overcurrent protection devices to achieve selective tripping. Fifthly, the NEC requires that all electrical equipment be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or Intertech. This listing ensures that the equipment has been tested and found to be safe for its intended use. When selecting overcurrent protection devices, it is important to choose devices that are listed and labeled by a recognized testing laboratory. Sixthly, regular inspection and maintenance of overcurrent protection devices are essential for ensuring their continued reliability. These should be inspected periodically to ensure that they are not damaged or corroded. Circuit breakers should be tested periodically to ensure that they trip properly when an overcurrent condition is detected. Any damaged or malfunctioning overcurrent protection devices should be replaced immediately. Seventhly, it is important to be aware of the potential for arc flash hazards when working with electrical equipment. Arc flash is a dangerous phenomenon that can occur when a short circuit or other fault creates an electric arc. Arc flash events can generate extremely high temperatures and pressures and can cause severe burns, injuries, or even death. When working on or near electrical equipment, it is important to wear appropriate personal protective equipment, such as arc-rated clothing, gloves, and face shields. Eighthly, the NEC is updated every 3 years, so it is important to stay current with the latest requirements. The NEC is a complex and comprehensive document, and it is essential to have a thorough understanding of its provisions to ensure the safety of electrical installations. Consider the scenario where a 200 amp feeder supplies multiple 100 amp panel boards. In this case, each 100 amp panel board would still require a 100 amp fusing at the point where it is connected to the 200 amp feeder. This is because each panel board is considered a separate load, and each load must be protected against overcurrent. In addition, the 200 amp feeder itself would need to be protected by a 200 amp overcurrent protection device at its source. This overcurrent protection device would protect the feeder conductors from overloads or short circuits that may occur downstream. When dealing with multiple panel boards, it is important to consider the total load on the feeder. The total load on the feeder must not exceed the ampacity of the feeder conductors or the rating of the overcurrent protection device. If the total load exceeds these limits, the feeder conductors must be upgraded or the overcurrent protection device must be derated. Now let's talk about some common mistakes that people make when installing feeder overcurrent protection. One common mistake is to use the wrong size overcurrent protection device. As mentioned earlier, the overcurrent protection device must be properly sized for the application. Using an overcurrent protection device that is too large can allow the conductors to overheat and potentially cause a fire. Another common mistake is to use the wrong type of overcurrent protection device. Fuses and circuit breakers have different characteristics and are suitable for different applications. Using the wrong type of overcurrent protection device can result in inadequate protection of the electrical system. A third common mistake is to install the overcurrent protection device in the wrong location. As mentioned earlier, the overcurrent protection device should be located at the point where the feeder receives its supply. Installing the overcurrent protection device in the wrong location can result in inadequate protection of the electrical system. A fourth common mistake is to neglect the coordination of overcurrent protection devices. As mentioned earlier, coordination of overcurrent protection devices is essential for ensuring selective tripping. Neglecting coordination can result in unnecessary disruptions to the electrical system. A fifth common mistake is to fail to properly inspect and maintain overcurrent protection devices. As mentioned earlier, regular inspection and maintenance are essential for ensuring the continued reliability of overcurrent protection devices. Failing to properly inspect and maintain overcurrent protection devices can result in inadequate protection of the electrical system. Finally, let's discuss the importance of documentation. It is essential to keep accurate records of all electrical work, including the size and type of conductors, the rating and location of overcurrent protection devices, and any coordination studies that have been performed. This documentation can be invaluable for troubleshooting problems and ensuring that the electrical system is properly maintained. In addition to the specific requirements for feeder overcurrent protection, there are also general requirements for electrical safety that must be followed. These requirements include the use of proper grounding techniques, the proper installation of wiring devices, and the use of appropriate personal protective equipment. By following all applicable electrical codes and safety standards, it is possible to create a safe and reliable electrical system. Remember, always consult with a qualified electrician or electrical engineer to ensure that your electrical system is properly designed and installed. Electrical work can be dangerous, and it is best left to the professionals. In conclusion, understanding and implementing proper feeder overcurrent protection is paramount for ensuring the safety and reliability of electrical systems. By adhering to the requirements of the NEC and best practices, electricians and other qualified professionals can help prevent overloads, short circuits, and other electrical hazards that could lead to equipment damage, injuries, or even fatalities. Always prioritize safety and seek expert guidance when working with electrical systems.